Hello and welcome to the wolfSSL live webinar, everything you need to know about DTLS 1.3, present by wolfSSL engineer Julius. My name is Shizuka and I'll be moderating this webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channels shortly after the presentation. I invite you to follow us on Twitter at wolfSSL, as well as our other socials. Also, feel free to email us if you have any additional questions. And now I would like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfcrypt with DO-178 support, HIP certification, and the HIPS Ready offering, MQTT up to the B5 specification, SSHB2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrapper and JSSC support, and commercial support for core. All of these offerings are accompanied by through maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Julius to talk about the DTLS 1.6.
Thank you, Shizuka. So I would also like to just show everyone that we have a very wide offering of products, a wide range of products, and using wolfSSL, you can gain access to everything here, as well as to comment about DTLS. It can be integrated with hardware security modules or trusted platform modules using wolfTPM and our PKCS 11 support, as well as wolfSSL is dual licensed. We're open source through GPL v2 and a commercial license. All of our code and all of our tools and products and projects are available on GitHub. You can inspect the code and run it for yourself, run all of our examples, and you can see it all for yourself. So just a little bit about me. My name is Juliusz Sosinovic. I'm an engineer at wolfSSL. I'm situated in Warsaw, Poland, and I'm going to talk to you about DTLS 1.3. So just a quick summary. DTLS stands for Datagram Transport Layer Security. Datagrams are connectionless packets sent over networks. They are single messages used by higher layer protocols. And in short, DTLS is for UDP, what TLS is for TCP. So our agenda for today is going to be DTLS basics, where I'll talk about what DTLS is and when and why you should use it. A comparison between DTLS 1.3 and DTLS 1.2. Some examples using wolfSSL. We will also be doing some network overview, some analysis in this section. Some examples for code. We will talk about some code snippets and how to integrate DTLS into your applications and projects. And at the end, we will have a Q&A session where I will answer your questions about DTLS. So DTLS basics. A short history of the DTLS implementations and RFCs. DTLS was always defined as a delta to the corresponding TLS specification. The numbering started at 1.0, but 1.1 was skipped so that DTLS and TLS would use the same number so that it would be easier to correlate them. Version 1.0 and 1.2 differ just mainly by the secure ciphers in 1.2, but the difference between DTLS 1.2 and 1.3 is pretty big. It's a very big step forward in security, efficiency, and features. So why shouldn't you use TLS instead of DTLS? So TLS requires reliability and an ordered delivery. This requires an entire TCP implementation, for example. You need some kind of a reliable protocol underneath TLS. And this imposes an overhead in latency, bandwidth, and resource usage. But different types of applications don't require reliability or ordered delivery. They have other priorities like minimizing latency and minimizing resource usage. So TLS would be bad for example, real-time streaming, online gaming, battery-powered devices, and resource-constrained devices. So this is where DTLS steps in. DTLS is defined as a delta from TLS. It reuses the well-established cryptographic primitives and the TLS implementation itself. This way, DTLS benefits from work being done on TLS. This includes extensions, RFCs developed for TLS, and this is a major security and feature advantage for DTLS. The same work that's being done on TLS extends to DTLS. So how does DTLS accomplish all of this? DTLS provides retransmission and reordering, but only for the setup, the handshake process itself. But this does not extend to the application data, so there's no overhead for application data. It's the same as using a regular datagram. Application protocols must implement their own reliability and their own ordering measures if that is something that's important for the application itself to function correctly. And DTLS uses explicit numbering for datagrams, for encryption and decryption. This accounts for packet loss, for reordering, and for any kind of duplication that might happen on in the network between the peers sending messages to one another. And yeah, just to recap, DTLS does not provide reliability or ordering for application data. So in what cases is DTLS a good idea? Securing UDP-based applications or other datagram protocols, real-time data communications, when you have tight resource limits, such as tight limits on bandwidth or, for example, on-device memory, using DTLS, then you can omit or you can scrap the TCP implementation, which is also it's not a small protocol. And other lightweight protocols, for one example would be VPNs, where you don't want to add any extra overhead or reliability on top of whatever the host is already doing. And there are also many other scenarios or applications where you might consider DTLS to be more relevant than TLS. So a comparison with unsafe device. So there are many embedded devices that do not use TLS or DTLS. They use their own protocol to transfer data directly using a plaintext UDP socket or other datagram socket or network layer. While these devices meet the functional requirements of their specification, security is increasingly being demanded as a requirement, and these devices can no longer ignore the fact that they are transmitting over plain text without any security enforcement. In this case, DTLS helps secure such a protocol. DTLS provides security through authentication, confidentiality, and integrity. What we mean by this is, for authentication, we verify that the peer is the intended recipient. This is done using X509 certificates. Confidentiality is hiding the contents of the communication from third parties using encryption. And integrity detection that the communication has not been tampered with. This is accomplished using AAD and the transcript hash, and there are also other features in DTLS that help ensure all of these security features. As I stated, it is now taken for granted that these security features are included as a basic feature for most connected equipment, and fewer devices are able to ignore this security requirement, and it is becoming more likely that they will be less desirable in the market compared to devices that do offer these security guarantees. So now we will talk about the comparison between DTLS 1.2 and DTLS 1.3. DTLS 1.3 builds on top of TLS 1.3, which is very modern, it's a faster and it's a safer cryptographic protocol. So how are the older specifications, how are the older algorithms and protocols unsafe? So one of the first step that DTLS 1.3 does to make it safer is by removing obsolete cryptographic primitives. SHA-1 collision attacks have been proven, they are now possible. MD5 collision attack has been published in 2008. So MD5 is an obsolete hash. It has been considered unsafe for many years now. There have been attacks discovered against RC4. DES and triple DES has been deciphered in tens of hours, and the security rating is much lower than other comparable symmetric cryptographic algorithms. And AES-CPC, just plain AES-CPC, there have been padding oracle attacks discovered, making it also not a suitable measure for the open internet. So another way that DTLS enforces better security is that it has completely removed static key exchange modes. So this means that every single session, every connection will have a new key, and this guarantees perfect forward secrecy. How? This is accomplished by by negotiating a new key every single time, and the attack vector that is described, or that perfect forward secrecy guy protects against is, for example, you have a server and the hard drives of the server are being discarded. They are being discarded in an unsafe manner. An attacker gets access to these discarded servers, and this way, for example, the RSA private key is compromised, and the attacker has been documenting, has been storing the contents of past communications, and then since the communications are all based on static key exchanges, with just having that one RSA private key, they can decipher all past communications. And one caveat of this in the DTLS 1.3 or in TLS 1.3 is that you can still use a static key exchange in the pre-shared key in the PSK. It's not recommended, but it's an option where you can use the pre-shared key directly to generate cipher material for the connection. So TLS 1.3 is more modern. It uses only AEAD ciphers. These are authenticated encryption with associated data. This provides authentication, tamper resistance, and confidentiality all in one cryptographic algorithm, all in one very optimized algorithm as well. These algorithms, for example, AES-GCM can be implemented or is implemented inside many processors and CPUs, making it extremely efficient and extremely fast at what it does. Another example is AES-CCM, and another one that is particularly good for small devices, for resource-constrained devices, ChaCha 20. and poly 1305. This algorithm is very good without any optimizations. It can be very fast, and it can compete with AES when you cannot have hardware optimization or only generic hardware optimization for your algorithms. Okay, so another way that DTLS is safer is we're going to show here a comparison between the 1.2 handshake and 1.3 handshake. So in the TLS 1.2 handshake, the entire handshake is done in plain text. Everything is out in the open, and all the information about who you're talking to, what you're talking about, and what you want from the connection itself is all out in the open. So an adversary, someone can sniff these connections, and they can look at the certificates, they can look at the server name indication, and they can see what websites you're accessing. They can take a look at the certificates, and they can figure out who's talking to whom, right? And in TLS 1.3, everything is encrypted past the initial client hello and the server hello. These two first messages are only in plain text because they are used to establish the cipher material, the cryptographic keys that are used for the encryption of the further stages. The only thing left in the client hello, the biggest extension in the client hello left that is sent in plain text is the server name indication. But in TLS 1.3, we have something called the encrypted client hello. It's a new extension for TLS 1.3 only, where you can encrypt the client hello, and that's also something that wolfSSL can support. So also, maybe we'll go back one slide just to mention this. As we can see here, the connection or the handshake is also much shorter. In TLS 1.2, the handshake consisted of 2 round trips at least, right? Because you need the first round trip is the client hello and the server hello flight, and the second round trip is the client's certificate flight along with its finished message, and then the server replies with the changed cipher spec and the finished message as well. And only after that, the peers can start talking to each other, can start transmitting application data. In TLS 1.3, the handshake is shortened to just 1.5 round trips, and this makes it obviously faster because we have fewer messages to wait for, and this translates to a faster handshake time. As we can see here, when the network latency approaches, it's the TLS 1.3 handshake is always much faster, but it makes a difference in the higher speeds. So the TLS 1.3 handshake is up to 33% faster than the TLS 1.2 handshake. So with these shorter handshakes for TLS 1.3, we require fewer round trips before we can start sending application data. TLS 1.2 requires 2 full round trips before application data can be sent, while in TLS 1.3 we have the full application data can be sent in just one round trip, after just one round trip, right? Because the client and the server can start sending data immediately after sending their finished messages. So the server has something called the 0.5 round trip time application data, and the client can start sending after just one round trip, as compared to the 2 round trips necessary for TLS 1.2. And a third way to make sending data even faster is the 0 round trip time application data. So TLS 1.3 introduced 0 round trip time data, or early data, and it can be sent, obviously encrypted, immediately with the client hello message when resuming a previous session or when you are establishing a session using out-of-band PSK data. But one thing to note for zero round-trip time or early data is that it does not guarantee perfect forward secrecy. As we've discussed before, perfect forward secrecy is using new keys for every single connection. The cipher material used to encrypt the early data depends on the cipher material of the previous connection or on the out-of-band PSK data, which can be static and can be a source of lack of perfect forward secrecy. So in summary, DTLS 1.3 specific improvements are safer, faster, and more efficient. And let's take a look at some of them right now. Message number encryption. So messages, the message sequence numbers are now encrypted, so it's much harder to do traffic analysis. Sequence numbers are no longer transmitted in plain text, making it harder to follow connections by a third party that is sniffing the communications between peers. Another new feature of DTLS 1.3 is the unified header. It's a new, very efficient header that can be as small as 2 bytes. So here we have the exact specification of the unified header. The first byte is the identifier. It identifies the packet as a DTLS 1.3 record, as well as it says how long the unified header is. So the first 3 bits are static, they're fixed. They're used to check whether or not this is a DTLS 1.3 unified header. The 4th bit presents whether or not the connection ID is present. The length of the connection ID is negotiated during the handshake, during the initial messages. The 5th bit describes how long the sequence number is, either 8 or 16 bits. The 6th bit states whether or not the length of the datagram is present. If the length is missing, then it is assumed, or the length of the message is implied to be the rest of the datagram message. And the last 2 bits signify the epoch number. So how can the unified header be only 2 bytes? So if the connection ID is not being used and the sequence number is 8 bits and we're not using the length field, then it's just the identifier byte, the first octet, and then the second octet is going to be the sequence number, the 8-bit sequence number. And that way you have a very small overhead for the DTLS protocol for your application data. There's only 2 bytes on top of whatever padding or encryption metadata is appended to your data. Another new feature of DTLS 1.3 are the explicit acknowledgements. This is a special new handshake message introduced in DTLS 1.3, acknowledgements or ACKs for short. Here we'll see an example of how ACKs work. Let's say the client sends 3 handshake messages and the second handshake message is dropped, or for some reason it just doesn't arrive at the server. So the server detects an out of order packet. The third packet is sent before we receive the second one, and we know the order of the packets is well defined, so we know whether or not we're missing a packet. And instead of waiting for the client to time out and retransmit its entire previous flight, wasting time and valuable bandwidth, the server sends an ACK for the messages that it did receive. That way the client can immediately replay the dropped message as such. The client receives the ACK that the server received the first and the third message, and it only retransmits its second message. This way we're not wasting bandwidth, and we're also saving time in the process. So using the explicit acknowledgements also saves bandwidth a lot. By using ACKs, we can, as I stated, we can shortcut the retransmission timer, and we can make sure that the peer only sends what's necessary. So without acknowledgements in DTLS 1.2, we had to resend the entire previous flight of messages to notify the peer that a record was dropped or reordered, and the peer had to replay the entire or retransmit the entire previous flight because it didn't know which message was dropped exactly. So both the server, or in our previous example, the server would have to retransmit its entire previous flight if it wanted to shortcut the retransmission timer, and then the client would also send all of its previous flight, which would lead to a lot of wasted bandwidth. And acknowledgements make this simpler and faster with no unnecessary data being sent between the peers. DTLS 1.3 also has built-in connection ID support. So what's the benefit of using connection IDs? It allows you to decouple IP addresses from the connection by using the connection ID instead of an IP address or an IP tuple to identify traffic. You can multiplex or you can decouple the IP addresses by being able to send from a different network interface or being able to reconnect and still maintain the connection without having to perform a new handshake or a new connection. You can also multiplex over a single IP if you can't, for example, your device does not give you the ability, your network does not give you the ability to multiplex over the network, then you can use the connection ID to recognize the traffic. Also, no new handshake on IP changes. So long-standing connection of IoT devices, for example, behind a NAT or whatever other device that experiences IP address changes. With the connection ID, you don't need to perform an entire new handshake for that. You can just piggyback off of the previous one, just resume where you left off. So DTLS 1.3 also introduces, or maybe not introduces, but another major feature is the stateless operation. How DTLS 1.3 is able to perform statelessly. It performs a return routability check for the peer that it received a message from using the TLS 1.3 hello retry request message with a cookie extension. And this is done to mitigate amplification DDoS attacks against DTLS or public DTLS servers. So the way that the hello retry request message checks for return routability with the extension is, in this example, the client first sends the client hello without a valid cookie. The server recognizes that this is a plain client hello. It does not contain the cookie yet. It responds with the hello retry request with a cookie extension without saving any state in the meantime. This operation can be done per message received, and there's absolutely no state being maintained between receiving the client hellos. And then the client responds with the client hello with the cookie extension. This way, the server can verify that this is a valid client, that this is a valid peer that can respond to us. This is not an off-path attacker sending random client hellos to us. And then the rest of the handshake, as previously shown, can continue. The advantage for this mode of operation is that the server operates statelessly until it receives a valid cookie in the client hello. And this may be dynamically disabled for resumption if you would like to allow for resumption. A reason why you might want to disable this check for resuming connections is to be able to use the 0 round trip time or the early data, as discussed before. If you would have to do this handshake or this cookie handshake before doing the proper DTLS handshake, then the server would not be able to store or actually decrypt any of the early data that it receives, because it's not storing state before it sees that the peer is a valid peer that has responded with a valid cookie. Another new exciting addition in DTLS 1.3 is post-quantum cryptography support. So the issue with post-quantum cipher suites in DTLS is that they don't fit inside the network MTU. As we can see here, the key share extension size of Kyber level 1 is 800 bytes. That's fine. That will fit inside the 1500 byte MTU for most UDP networks. But for Kyber level 5, the key share is 1574 bytes. And this is just the key share without the other necessary information of the client in the client hello and the UDP headers that obviously also need to be included inside this MTU. The way that we've solved this is by allowing the client to first send the client hello, but with an empty key share. We send the empty key share so that we guarantee that the client hello is unfragmented, because since the server is operating statelessly, we don't want to allow random peers to perform resource exhaustion attacks or other DDoS attacks on DTLS servers. This way, the entire client hello can be validated by a stateless server. And when the server receives a valid client hello that's unfragmented, it responds with the hello retry request including the cookie extension to perform the return rootability test. And it also includes the available post-quantum cipher suite key share. And then once the client receives this information, the hello retry request is also used for key negotiation in TLS 1.2. So we're doing the return rootability test and key negotiation in the same message. And once the client receives this, the client includes the entire cookie in the first fragment of the client hello. This way, the server can confirm that from just this one fragment that the peer is legitimate, and it enters stateful parsing. Once it enters stateful processing, the server can now store and process the remaining fragments of the client hello message. So this is how we've solved the issue of fragmenting the initial client hello, but not exposing public DTLS servers to DDoS attacks or resource exhaustion attacks. And then obviously after sending the fragmented client hello, the rest of the handshake can continue as normal. So obviously, another great feature of DTLS 1.3 is that it allows for version negotiation. The handshake itself has built-in version negotiation support, and this allows peers to establish a common version. And this is great for adoption of DTLS 1.3. It allows for a gradual upgrade to the ecosystem, and peers supporting both 1.2 and 1.3 can coexist, and you don't need to go from 1.2 or 1.3. You can support both of them while preferring 1.3, obviously. So now we'll take a look at some network analysis of DTLS 1.3 using wolfSSL, publicly available wolfSSL tools. So you can run all these examples for yourself as well. These are examples for Linux, Unix, or Mac machines. You first need to get wolfSSL. You need to clone it from our repository or download it from our website, wolfSSL.com. And then you just use the autogen script and configure wolfSSL so that it has enabled DTLS and DTLS 1.3 support, and then just compile it using make. You can use /configure --help to see all the numerous configurations that we support and what other features you might want to enable. So to run DTLS 1.3 or 1.3, yes, using the wolfSSL apps tools, just run in parallel the example server using -u to enable DTLS and -v4 to enable DTLS 1.3. And at the same time, in a separate window, in a separate terminal, you should run the client using the same options. And as before, you can use help to list all the other features that wolfSSL supports. For example, you can test out non-blocking with our apps. You can test out resumption, early data, and you can all take a look at this for yourself. So this is the expected output from the example apps. You can see that the negotiated version is DTLS 1.3, and we can see that the cipher suite is a TLS 1.3 cipher suite, and we also have the curve name specified that is used to negotiate the keys for the connection. And if you would capture the connection in Wireshark, it will look like a DTLS 1.2 connection at first, and then the remaining packets will look like just raw UDP packets because Wireshark currently does not identify them. It doesn't identify them because the DTLS handshake is encrypted just like in TLS 1.3. And once Wireshark does start supporting DTLS 1.3, it will be able to show them and hopefully also decrypt them so that it is easier for you to analyze the DTLS traffic. But we can take a look at the initial or at the first server hello. In the first server hello, we can see that this is the cipher suite chosen, as we saw in the output of the example app, the terminal output. We see that the key share is chosen. This is a extension for TLS 1.3 to make sure that that guarantees the perfect forward secrecy by using elliptic curves, for example, or elliptic curve cryptography to negotiate new keys for every connection. And in the supported version extension, we see that we are using or we're negotiating an unknown supported version, but this is an unknown version because Wireshark does not recognize this version just yet. FEFC is the special or is the magic number used to negotiate DTLS 1.3. So this is a comparison between the TLS 1.3 and DTLS 1.3 capture. We can see it's basically a one-to-one because DTLS builds on top of TLS. We can see fragmentation of the certificate message because we want to fit inside the MTU, which for UDP we're assuming is 1,500 bytes. And also an interesting thing to note is that the final finished message has to be acknowledged. It's not something that's shown in the handshake flow diagrams before or even in the specification, but the final finished message of the client needs to be acknowledged by the server. If it's not acknowledged, then the client will try to retransmit it and wait for the final acknowledgement. So now we're going to take a look at how you can enable DTLS inside your applications and projects. Basically, how can you go from an unsafe protocol that uses UDP directly to a protocol that uses DTLS on top of UDP? So there are quite a few embedded devices that do not use TLS or DTLS, but rather they use their own protocol. And as I stated before, such devices may have sufficient functionality. They might perform up to the requirements, but additional security is necessary, and it's increasingly being demanded as a requirement for anything that's connected. Here we have a basic example of creating a socket and sending something to a peer and then closing the socket. This is a very basic UDP socket. There's absolutely no protection for this whatsoever. We're just sending data, receiving data from the peer, and then closing the socket. That's it. So to enable wolfSSL on top of this socket, or to provide DTLS security for this socket, you first need to create the SSL context. You use the wolfDTLS client method. This selects the highest supported method, as well as it allows for downgrading so that you can connect to a DTLS 1.3 and 1.2 peer with the same connection. You don't have to have a dedicated server for 1.2 and a dedicated server for 1.3. We then load the certificate authorities, and then we create the SSL object. So once that's done, we then have to associate the SSL object with the peer that we want to send and receive from. We also have to associate the socket. So we have to set the file descriptor of the socket. And then we execute the handshake using wolfSSL connect. If you're using blocking sockets, then this will probably be just one call, and then the connection will be done. If you can use also non-blocking sockets. In that case, every time we want to write or read, but we can't because the network layer prevents us from doing that, we return control to the user, and then the user can wait for the socket to become free and call wolfSSL connect again until you finish the handshake. Then instead of writing and reading directly from the socket, you use wolfSSL write and wolfSSL read to transmit and receive encrypted and decrypted data. And then at the very end, we should call wolfSSL shutdown to notify the peer, the other party, that the DTLS session is terminating. This sends the close notify alert to the peer and allows the peer to close the connection, free up resources, and not wait for more data since it's not coming. And then we need to do the memory cleanup of the SSL and the context objects. With all of this, the DTLS with all of this, the socket is now protected using DTLS, and you no longer are susceptible to sniffing or fraud where the peer is impersonating someone else, even though it appears to be coming from a valid peer. You can still check it using certificates, for example. So this is how we provide confidentiality, integrity, and authentication for a raw UDP socket. More examples for how to use DTLS and more caveats and more edge cases, more scenarios are available in the DTLS directory of our wolfSSL examples GitHub repo. And in summary, DTLS 1.3 is a faster, safer, and more cutting-edge cryptographic standard when compared to DTLS 1.2. There are very few changes required for migration from 1.2 to 1.3, and we have full support of DTLS 1.3 in wolfSSL now. If you're interested, wolfSSL supports a very broad, very wide range of MCUs and operating systems, as well as many different development environments. Engineers, myself and my peers, are available to answer technical questions at support@wolfSSL.com. And obviously, we are open source, available on public repos on GitHub, so you can start your evaluation and development right away without having to wait on anything. You can go ahead, download the repo, and see for yourself everything that I've been talking about. So thank you very much. I think we can enter the questions and the Q&A portion of the webinar.
Thank you. So there is a question. Do you have a hardware crypto support for STM32H573?
For STM32H573. I don't know the exact crypto support off the top of my head, but we do support many STM microcontrollers. Yes, and using wolfSSL, you automatically get get all of our hardware support as well, hardware optimization and assembly optimization.
There's another question. It is okay to use GPL v2 version in embedded project if wolfSSL is linked to application binary as a separately built library, but the end application is one binary containing application specific code and a wolfSSL library.
So for GPL v2, it's definitely fine to use GPL v2 for development, but this sounds like wolfSSL is going to be included into your project, and I'm not an expert on GPL specifics, and definitely not a lawyer. But this sounds like it would violate the GPL, since you would need to release your end application as GPL as well, because whatever project includes GPL also needs to become GPL itself. So that would be fine for development and evaluation, but if you'd want to go commercial with that, then you would require a commercial license.
If you have any commercial license question, please email us at fax@wolfssl.com so we can assign to a sales director, and then you can talk to them and they can give you more details. And I do have another question. Does DTLS v1.3 require more resources, memory, CPU, processing power, and etc.?
Well, I would ask require more resources than what? If you're comparing it to just a plain connection, if you're using just the network layer directly with no security on top of it, then yes, DTLS 1.3 does require more resources. But okay, I see that the clarification, does it require more resources than 1.2? I think our benchmarks showed that the memory resource use is about the same. And it depends on what kind of ciphers you're using and what algorithms you're using.
And there is another question. There are a few ambiguities in the RFC. For example, the endianness of the counter input into Chacha poly for sequence number mask generation. How was your choice made, and what if the standards is clarified or other implementations choose the opposite?
So we had actually a very long debate on this. This is actually an interesting question. We had a very long debate on which endianness to choose for the Chacha poly counter in the record sequence number encryption. We just in the end we tried to we had to reference the Chacha specification or Chacha poly specification itself. So we had to go and reference another RFC. And our choice was to, I don't remember which endianness we chose, but basically just chose what the endianness was specified in the Chacha poly RFC. And if the standard is clarified, then we will obviously adhere to whatever errata are posted. But but if other implementations choose the opposite, then we will obviously have to discuss with them the motivation for choosing the opposite endianness.
There is another question. Is DTLS 1.3 in wolfSSL ready for HEPS 140-3 certification?
Yes, DTLS 1.3 when using a FIPS 140-3 certified wolf crypt is definitely ready for FIPS 140-3 certification. The FIPS 140-3 certification applies to the underlying cryptographic library wolfcrypt, which our wolfSSL DTLS implementation uses fully. So if you want to use DTLS in a FIPS 140-3 project, then you're good to go with wolfSSL. The only caveat specifically with FIPS 140-3 is that we're still waiting for our certificate, but hopefully that's coming soon. And once that arrives, DTLS is ready for FIPS 140-3.
There's another question. Does STM32CubeMX ecosystem support wolfSSL with DTLS 1.3?
I haven't tested this configuration myself, but I would imagine that if we do support the STM32 ecosystem and DTLS 1.3, I would expect it to work flawlessly inside the STM32 ecosystem.
There's another question. Is TLS v1.3 available in latest 5.6.x HEPS ready package?
Yes, it is available in the latest release. It's available in 5.6.4, which is the latest release, and was also available for a while before that. Both TLS 1.3 and DTLS 1.3 are available in the latest releases and in the latest FIPS ready packages.
And I do have another question. Apology if this was already covered. I missed the first part of the webinar. Is it possible to use DTLS over another protocol than UDP as long as it supports frames, datagrams, or are there other requirements?
Absolutely. You can use DTLS on top of any datagram protocol. And we're also testing our DTLS implementation on top of streaming protocols. So you could even use TCP or if your network layer provides a streaming interface, then you can also use wolfSSL DTLS on top of that. If you would be using a streaming interface, then obviously you would have to have the you can't omit the length field from the DTLS record layer from the unified header. But apart from that one requirement for when using a streaming protocol underneath DTLS, then you can use any kind of transport protocol for DTLS, since DTLS provides also does error checking itself, so that it makes sure that if any kind of anything weird happens on the network, then it can self-correct. It just rejects the message and makes sure that we can continue the connection, the conversation, even in the case of reordering, failure, or any kind of, for example, bits being switched. So UDP is not a requirement. It can be any datagram or even any kind of network layer or network protocol.
If there is no any other questions, think, there's another question. Any plans for IoT Safe and DTLS?
I know we do support IoT Safe in wolfSSL, but I don't know what the status is of using IoT Safe with DTLS. I'm not sure if we've done a demonstration, but I do recall IoT Safe being used, I think, for a TLS connection. And in that case, it's fairly simple to extend the TLS scenario, TLS use case to a DTLS version. But I don't know the current status of IoT Safe and DTLS. But that's a very interesting question too.
If there is no any other question, and thank you, Julius, for hosting the informative webinar, and everyone for joining the webinar today. Please don't forget to follow us on Twitter at wolfSSL, as well as the socials. And thank you again, and see you next week. And yes, you can get the presentation. I will post this recording to the YouTube channel shortly after this webinar, so you can access to the webinar. Thank you.
Thank you everyone for joining.